In this video, we're going to take a look at section R.7, which is on exponents. Now, you've already seen exponents in this class, but let me remind you of how exponents typically work. If you have something like this, excuse me, I wasn't ready, 3 to the 4th power, that means not 3 times 4, it means 3 multiplied to itself 4 times. And so when you multiply this out, you'll take 3 times 3, which is 9. This 3 times 3 is also 9. And then you multiply those together and you get 81. Now this definition only applies, it only makes sense if the exponent is a positive whole number. Then exponents can be thought of as repeated multiplication. But what we're going to be looking at in this section, as well as the topic that I just introduced here, is exponents that are negative whole numbers. So we won't be seeing exponents that are fractions yet. That comes later in the course. But in addition to exponents that are positive whole numbers, we will also have exponents that are negative whole numbers. So I want to talk about for a moment how those behave, because it's a little bit counterintuitive. What you probably would guess the answer should be is not necessarily what the answer actually is. So let me explain why negative exponents work the way they do. So we just established that 3 to the 4th power is 81. 3 to the 3rd power, if you multiply that out, you get 27. 3 squared, if you multiply that out, you get 9. 3 to the 1st power is just 3. It's just 3 one time. And so far, the definition that we used over here applies to all of these examples. But if I go one step further and go to 3 to the 0 power, the definition no longer really makes sense. How can you take 3 and multiply it to itself 0 times? Now you might guess that the answer to such a situation should be 0. If you have 0 3's, you just have nothing at all, but that actually is not the right answer. If we look at the pattern that is occurring here, each time I drop the exponent by 1, what's happening to my answer is it's getting divided by 3 from the previous answer, right? So 81 divided by 3 gets me to 27. 27 divided by 3 gets me to 9. 9 divided by 3 gets me to 3. So the pattern is really well established that when the base is 3, each time you lower the exponent by 1, you take the previous answer and divide it by 3. And that pattern should continue even as we go lower on our exponents. Even when this definition no longer makes sense, this pattern can still be applied. So to get this answer here, 3 to the 0 power, I go back to my previous answer, I divide it by 3, and I get 1 as my answer. So 3 to the 0 power is equal to 1, not 0 as you might have expected. And in fact, this will always be true. Any number to the power of 0 is equal to 1, except for, I guess, in full disclosure, I should say this, it's not going to come up in this section as you go through the homework or anything, but just so you're aware, 0 to the 0 power is actually undefined. So we don't really have an answer for that one. But any other number raised to the 0 power is equal to 1. Now what happens if you continue to go further down? So I drop the exponent by 1 again, I'll get 3 to the negative 1st power. What should that equal? A lot of students would guess that should equal negative 3, right? 3 to the 1st power is positive 3, so why wouldn't 3 to the negative 1st power be negative 3? But that doesn't fit this pattern, so it doesn't make sense as an answer. So let's apply this pattern yet again. I take my previous answer, which is 1, I divide that by 3, and I get a fraction of 1/3. So I don't get negative 3, I get 1 over positive 3 as my answer there. And if you went further, if you went to 3 to the negative 2nd power, I don't know if I left myself enough room to squeeze that on here, but 3 to the negative 2nd power, again, using this pattern, we take the previous answer, divide it by 3, and what you end up getting is 1/9. Right? So the pattern here for these negative exponents is that 3 to the negative 2nd power doesn't equal negative 9. It equals 1 over 3 to the positive 2nd power, which is 1/9. Right? So that's why negative exponents behave the way they do. All right, so I just wanted to get that out of the way so that we can look at these definitions, and when we get to this definition, you'll understand why it works the way that it does. All right. So what we're going to be doing in this section is having exponents interacting with each other. And so if you have two expressions, now the important thing here is that these have the same base, right? They both have a base of a, each being raised to a different power, and you are multiplying those together, then those can be multiplied into a single exponential expression by adding the exponents. So it's a little bit weird because here you're multiplying, but then when you put the exponents together, you add the exponents. But this is why the rule works this way. So if you have, let's say, 3 to the 4th power times 3 to the 3rd power, let's say. If you break this down using the basic definition of an exponent, that this is 3 multiplied to itself 4 times. 3 times 3 times 3 times 3. This is 3 multiplied to itself 3 times. And these two things are getting multiplied together. Sorry, that dot went a little bit lower than I wanted it to. Now I have 3 being multiplied to itself how many times altogether? 7. Right. And so instead of having to do it this way every time, we know there's a shortcut. We just take this exponent plus this exponent, and that gives me the new exponent. And the important thing here to notice is the base stays the same. Right? So this doesn't become 9 to the 7th power. That's a very common mistake. Students take 3 times 3 and think that's 9, and then add the exponents and get 7. That's not how it works. Right? The base does not change. All we do is add the exponents. That's it. And that's how you multiply those two together. I'm not going to go through a similar example for this rule, but it works in almost the same way. If you're dividing two things that have the same base, the base does not change. It stays the same. But this time we subtract the exponents. That's the shortcut. So we take the top power minus the bottom power. And that's how we get that. All right. So if you're multiplying two things together, you add the exponents. If you're dividing those two things, you subtract the exponents. The base has to be the same for that to work. All right. We'll see an example here in just a minute. But first I want to talk about the rule for negative exponents, which we just talked about at the beginning of the video. And we actually saw this in play earlier. We have 3 to the negative 2nd power equals 1 over 3 to the positive 2nd power, which is 1/9. That's just this rule here. All right, so if you have a negative exponent, if you flip it down to the denominator, that makes it a positive exponent. And positive exponents are better for us to work with. They're easier to evaluate. They're easier to work with. And so the rule we're going to be following here to simplify, and this isn't really spelled out anywhere, so let me put it here, because you won't see it in the directions, but this is what we want to accomplish when they ask us to simplify. One thing we want to accomplish is no negative exponents. So no negative exponents, so that means doing things like this to get rid of negative exponents. For these problems, now this might not be a universal thing that you can do all the time, but for these problems in section R.7, you should be able to rewrite it so there's just one of each variable. So in your final answer, you should be able to have it so there's only one x, one y, one z, one of each variable that's in the problem. And then the third thing you want to do is simplify or reduce the numbers involved. So if you have a 3 on the top of your fraction and a 6 on the bottom of your fraction, reduce those numbers so it reduces down to 1/2. And so if you do those 3 things, you'll get the answer you're supposed to get in the simplified form that it's supposed to be. For negative exponents, so I didn't quite finish talking about the negative exponents here. We have this other rule, and it's the same idea, but it's the other way around. If your negative exponent's in the denominator, you can flip that expression up to the top to make it a positive exponent. Right? So now this expression's in the numerator, and the exponent becomes positive when we do that. So that's how we get rid of negative exponents. Keep in mind, this does not get rid of negative numbers. So a lot of students get a little bit carried away with this rule and flipping things from one side to the other. So flipping things from the numerator to the denominator or vice versa. But that only affects the exponents. It does not affect numbers that are on the ground, if you will. So for example, if we have negative 3x squared, you cannot take this negative 3 and flip it down to the bottom and write that as x squared over positive 3. you can't change a negative number by flipping it to the bottom and making it a positive number. You can only change negative exponents. So you can do this. If we have negative 3x to the negative second power, we can flip the x to the negative second power down to the denominator. You can't do anything about the negative 3. You're just stuck with it. It's a negative 3 that'll stay on top, but the x gets flipped down to the bottom and becomes x to the positive second power. So exponents, we have some control over. You can change the sign of an exponent. You cannot change the sign of a number. All right, so keep that in mind as we look at some of these examples. All right, so here we want to multiply these two expressions together, and the base here, 6, is a number, so you have to be careful not to make this mistake. When we multiply these two things together, the base stays the same. You do not get 6 times 6, which is 36. A lot of students will do that, and that is incorrect. The way you multiply these together is by adding the exponents, and the base does not change. So to multiply these two together, we'll add these exponents. We have negative 4 plus negative 3, which add together to give me negative 7. Now, if you type that answer into Math Excel, this will not be correct because remember the rule I just talked about a moment ago. Right. To simplify, no negative exponents are allowed. So I need to rewrite this so that the exponent is not negative. To make this a positive exponent, we flip it down to the denominator. So think of this as a fraction. Think of it as being over 1. We're going to flip the 6 down to the denominator, and that'll change the sign of my exponent from negative 7 to positive 7. And because I'm emptying out the numerator, I have to leave a 1 behind there. And so we get 1 over 6 to the 7th power, positive 7th power. And don't bother multiplying that out. Don't plug it in your calculator. This is going to be some ginormous number, and Math Excel doesn't want that anyways. It wants you to leave it as an exponent. All right, so a couple important things there. The base stays the same. Deal with that negative exponent, make it a positive exponent. All right, let's take a look at this example. Again, we have a base that's a number. That's when we have to be extra careful about that. We don't get 5 divided by 5, which is 1. That's what some students will put on the test. I guarantee it, even though I mention it in class, I'm mentioning it in this video, I'm going to have students, when they take the test, they're going to make that mistake. It happens every semester. The base stays the same. So the base is 5. The base will stay 5. And the way I divide these two expressions is I simply subtract the exponents. That's all I have to do for that division to take place. So it'll be the top power, which is 6, minus the bottom power, which is negative 5. And because we're getting a double negative, now I'm subtracting here, but because I'm subtracting a negative number, it becomes a plus, right? And so we will get 5 to the 11th power. And because that's not a negative exponent, there's nothing else for me to simplify here. So that would be the final answer. All right, let's take a look at another example. All right. So this time we have variables, and this is going to be, I think, a little bit, even though we think of variables as making things more difficult, I think this problem's a little safer because we're not tempted to actually multiply those together as numbers. So when it's a variable, most students are fine with keeping that variable the same. So to multiply these two together, just like we did this example here, it's the same exact kind of problem. The base will stay the same, so the base will stay x, and I will add the two exponents together. 6 plus negative 9 is going to equal negative 3. Because I have a negative exponent, I need to make that positive. I have to simplify it by making it positive. So I'm going to flip that down to the denominator and make it a positive 3. Because nothing will be left in the numerator, I'm going to put a 1 there as a placeholder, and that would be my final answer. Let's do the same thing here. Again, it's going to follow the same pattern as the previous example we just did with the number 5. The base here is g. That'll stay the same. And the way I'll divide these is by subtracting. So I'll have 6 minus negative 8. We'll get the double negative there, which makes that positive. So we're going to get g to the 14th power. Since the exponent's already positive, I just leave it the way it is. So I'm meeting all the criteria. No negative exponents, just one of each variable, just one g. And if I had some numbers to simplify, I would, but there's nothing else to simplify here. All right. Now these examples are going to get a little bit more complex as we go further into the section. So here what we want to do is multiply these two expressions together. And the way I like to describe this is it's not really combining like terms. That's the wrong way to describe it, even though some students might call it that. What you should do is multiply together what goes together, right? Because what's happening here is everything's being multiplied together. This is -5 times x to the -4, and that's being multiplied to 7 times x to the -4. So it's all multiplication, and something that you should know about multiplication is it's commutative, meaning we can change the order that we do it in and still get the same answer. So if I'm multiplying four things together, it doesn't matter what order I multiply them together in. And so I'm going to rearrange these. So I have -5 times 7. I'll put the 7 first, and then I'll put the x's last. And that way the things that will multiply together are next to one another, and then I can go ahead and simplify by actually multiplying them together. So -5 times 7 will be -35. And then the x's can be multiplied together because they have the same base, and so I'll have the base staying the same. I'll add the exponents, -4 plus -4, which will give me -8. All right, so ultimately you just multiply together what goes together. Most students don't bother writing out the problem in this much detail, and honestly, I usually don't bother doing that either, just doing it this one time as a courtesy so you can kind of see how the math behind it works. But what I do with these problems is, as I said at the beginning, multiply together what goes together. The -5 and the 7 go together, and I multiply those together to get -35, and then the x's go together, and I get x to the -8. And so I really just kind of skip to that result. Now, if you type that into Math Excel, it's not going to be correct because it doesn't meet all the criteria, right? So remember, the final answer should have no negative exponents, one of each variable, and simplify or reduce the numbers. We have just one of each variable, so we've met that criteria. We just have one x, but it has a negative exponent. So we need to simplify that by flipping it down to the denominator. So think of this as being over 1, and I already addressed this situation earlier in the video. You cannot change a negative number. We're stuck with the -35. You cannot flip it down to the bottom to make it a +35. The exponent on the 35 is a 1, which we want to leave as a 1 because it's a positive exponent. So if I insisted on flipping the 35 down to the denominator, not only would it still be negative, it'd still be -35, but then the exponent would become -1 because that will switch the sign of my exponent if I flip it down to the bottom to a negative exponent, which I don't want. So you want to leave the 35 on top. And it's negative. There's nothing you can do about it. You're stuck with a negative answer. But the x can be flipped down to the bottom. And by doing so, we'll change the sign of the exponent from -8 to +8, right? We can change negative exponents. We cannot change negative numbers. So this would be my final answer, and it meets all of the criteria, right? One of each variable, no negative exponents, and we are simplifying or reducing the numbers. All right, let's look at another example here. All right, so again, getting a little more complicated. This one's division. And so let's go ahead and deal with, now the three criteria are no negative exponents, one of each variable, simplify or reduce the numbers. They don't have to be done in that order. Those are just the three things that have to be accomplished. The order doesn't matter how you get them done. So even though that's a negative exponent, I'm not going to sweat it right now. I'm just going to deal with combining the variables together. So we're dividing, so let's divide the x's, and we'll do that by following the rule. The base stays the same, so the base will still be x, and you take the top power, which is 4, minus the bottom power, which is -3. We'll do the same thing for the y variable. The base stays the same. We take the top power, which is 5, minus the bottom power, which is 9. If you do it in that way, that keeps it keeps the process as simple as possible. Now, some students have learned, like, you take the bigger number minus the smaller number. That would work okay for the y variables. And then you put the answer where the bigger number was. That's a shortcut you can use, and that would work okay for the y variables, but I would hesitate to do that for x, because when you start throwing negative numbers into that, it makes it a lot more confusing. So if you want to keep it simple, it's always top power minus bottom power, and you always write the answer on top. Sorry, that did not make a very good fraction bar there. Let's try it like that. And we'll still have the negative 24 on top, and we'll still have the 18 on the bottom. Right? So top power minus bottom power, write the answer on top, see what you get, and then deal with that in the next step. Right? So we're going to have 4 minus negative 3. That's going to become plus. So we get negative 24, x to the 7th power, because 4 plus 3 would be 7, y to the negative 4th power over 18. All right, so we have a negative exponent to deal with, and so we will drop that to the denominator to make it a positive exponent. So we'll have negative 24 x to the 7th power over 18 y to the 4th power. And so we have one of each variable. We have no negative exponents. Remember, you can't do anything about this negative number. You're stuck with negative 24. You can't make it a positive 24. But what we can do with these numbers is reduce. So we can divide a 6 out of both of these, right? Divide the top number by 6, divide the bottom number by 6, and we're going to end up with negative 4 x to the 7th power on top. Let me try that again. I don't really like how that 7 looks. Let me try that one more time. Okay, and then on the bottom we'll have 3 y to the 4th power. And this meets all the criteria. No negative exponents. Again, it's okay to have a negative number. The negative 4 is fine. None of the exponents are negative. One of each variable, and we simplified and reduced the numbers. So that's exactly what you want your answer to look like. All right, so there's a few more rules for exponents to make things even a little bit more confusing. These are called the power rules. All right, so here we have one base of a, change colors here, one base of a with two exponents acting on it. So you're taking one power, raising it to another power. So whenever that happens, you multiply the exponents together. M times n. The base stays the same. All right, so the reason that's happening, let me just give you a quick example why that has to happen. Let's say we have x to the 4th power raised to the 2nd power. All right, this exponent of 2 is telling me to take the base and multiply it to itself twice. All right, in this case, my base is the x to the 4th power. So I take x to the 4th power, multiply it to itself twice, and if I write it out like that, and I'm multiplying it to itself twice, this is the case where I want to add the exponents. 4 plus 4 is going to give me 8. And so my final answer is x to the 8th. The shortcut is I can get that answer even more quickly by just multiplying these two numbers together. 4 times 2 is how you get the new exponent of 8. So instead of writing it out like this and going the long way around, we have a shortcut directly to the answer. The shortcut is you multiply the exponents together to get the answer you're supposed to get. All right, so that makes things a little more confusing because some cases we add the exponents, other cases we multiply. We have to be careful about when we do which. These other two rules tell us that if you have an exponent outside parentheses and the two things in the parentheses are being multiplied together, you can distribute the exponent to those two things. And so in this case, they're factors. So if they're being multiplied together, we call them factors. So you can distribute the exponent to each factor inside the parentheses. This rule does not work if you're adding the two together. So if you had a plus b to the n power, you cannot distribute the exponent to those two things. Those are called terms, right? So if you're adding two things together, those are terms. You cannot distribute the exponent to terms. You can only distribute them to factors, to things that are being multiplied together, right? Which is all you should see in section R.7. So you shouldn't even come across a case like this. But later on in chapter 4, we will see things like that. And you want to keep in mind that if you're adding, you cannot distribute the exponent, only if you're multiplying or if you're dividing, right? So if you have a fraction, this exponent can be applied to the top and bottom of that fraction. And that fraction really is a division. Okay, so let's take a look at some examples of using the power rule. All right, so here we have negative 8, d to the negative 3rd power, h to the 4th power, k, and that whole thing is being raised to the negative 2nd power. All right, so we're going to take this power of negative 2, and we are going to distribute it into the parentheses because all these things are being multiplied together. So as long as it's all multiplication, you can distribute that exponent to everything inside the parentheses. So we're going to have negative 8, make sure to include the negative here, raised to the negative second power. We'll have d to the negative third power raised to the negative second power. We'll have h to the fourth power raised to the negative second power. And then we'll have k raised to the negative second power. So I'm applying that power of negative 2 to each thing inside the parentheses. So let's go ahead and deal with the variables first, and then we'll talk about the number here at the beginning of the expression. So here what's going to happen, because you have one base with two exponents applying to it, this is the case where you want to multiply those two exponents together. You don't want to add these, you want to multiply. So if it's one base with two exponents, you multiply the two exponents. If it's two bases, each with their own exponent, if it looked like this, then I would add these together. And I would get d to the negative fifth power when I did that. So if each exponent has its own base, you're going to add the exponents together. But if it's the two exponents on the same base, that's when you multiply. That's the easiest I think I can explain that rule to help you remember when it's adding and when it's multiplying. So we're going to get d to the positive 6th power, because negative 3 times negative 2 is positive 6. We'll get h to the negative 8th power, and we'll get k to the negative 2nd power, because again, we're going to multiply. 1 times negative 2 gives me negative 2. And then I'm just going to copy this number down, because we'll deal with it in the next step. All right, so the next step is, now that we have just one of each variable, and we've simplified the exponents on each of those variables, we don't want negative exponents in our final answer, which means this needs to be fixed, this needs to be fixed, and this one needs to be fixed. So all of those are going to get moved down to the denominator. All right. The d to the 6th power will stay on top because it's already a positive exponent. So we're going to get d to the 6th power over negative 8 to the 2nd power. So notice what I did there. The exponent will become positive when it gets moved to the denominator, but the number doesn't change sign. So remember, anytime we're flipping things around, you can't change the sign of a number. You can only change the sign of the exponent. So the exponent becomes positive 2, but the number inside the parentheses is still negative 8. And then we'll get h to the positive 8th power, because again, change the sign of the exponent to positive 8. And then k to the positive 2nd power. And now we can multiply this out. Negative 8 to the 2nd power is going to be positive 64. And so my final answer will be d to the 6th power over 64, h to the 8th power, k to the 2nd power. And that meets all the criteria, right? We have no negative exponents, one of each variable, and we simplified the number. 8 squared, we wrote that as 64. All right, let's take a look at this example. We have 81 u to the 3rd power, v to the negative 3rd power, over 3 u to the 4th power, v to the negative 2nd power, and that whole fraction is being raised to the negative 5th power. So you might be tempted to do the same thing we did last time and distribute the power of negative 5 into the fraction to get started. But I think that's a bad choice, because what we want to do first here is simplify what's inside the parentheses. Now we couldn't do that on the last example because there was nothing to simplify inside the parentheses. But if you can simplify first before distributing an exponent, that's usually your better course of action. So let's go ahead and reduce all this. I wouldn't worry about negative exponents yet. I would just worry about getting one of each variable. That's the best thing you could do. If you have a negative exponent, just leave it, and then at the end we'll figure out what to do with it. So we're going to go ahead and start by, I'm going to reduce the numbers here. So we have 81 and we have 3, and so that reduces to 27, right? So the 3 cancels out with the 81, it leaves me with the 27 up here. For u, we're going to take, remember the base stays the same, and we're going to take the top power, which is 3, minus the bottom power, which is 4. We'll do the same thing for v. The base stays the same. We'll take the top power, which is negative 3, minus the bottom power, which is negative 2. So be careful. A lot of negative signs there, right? Negative 3, negative 2, and you're subtracting. And then let's simplify that before we bring this negative 5 back into the picture. So we're going to have 27 u to the negative first power v to the negative first power, because minus negative 2 becomes plus 2. And so I'm going to get negative 1 there also. This is now going to get raised to the negative fifth power. And now that I've simplified it, it's very similar to the problem that we just looked at. Right? Didn't start off that way, but now that I've simplified it, it really is a repeat of the problem that we just did. Now we're going to take this exponent of negative 5. We're going to distribute it to each thing inside the parentheses, each factor, because they're all being multiplied. So I'll continue up here. We'll get 27 to the negative fifth power. We'll get u to the negative first power raised to the negative fifth power. And we'll have v to the negative first power raised to the negative fifth power. All right, so we'll copy down the 27 to the negative fifth power. Here we'll multiply these together because it's one base with two exponents, so we want to multiply, and we'll get u to the positive fifth power. So you see, by waiting, the negative exponent resolved itself there. If I would have worried about it here, and then I apply the power of negative 5, I would have just got it back again. I would have had to flip it again. So instead of flipping it here, getting a negative exponent and having to flip it back, I let the negatives cancel each other out, basically. Same thing here. We're going to multiply these two together. We get v to the positive fifth power, so I don't even have to worry about the negative exponent there. All right, but I do have a negative exponent on this number, so we're going to have to take care of that by flipping it down to the denominator. And so we'll have u to the fifth power, v to the fifth power, over 27 to the fifth power. Now, I'm pretty sure MathXL does not want you to type in, or MyMathLab, if somebody else is watching this video and you're using MyMathLab, I don't think they're going to want you to take 27 and actually raise it to the fifth power, because that's going to be a really big number. And so most likely what they're going to want you to do is to simplify this number by having the base be in the lowest number possible. So we can rewrite 27 as 3 to the third power. And maybe I should have done that up here to begin with, right? We could have wrote 81 as 3 to the fourth power and then dealt with these as exponents instead of dealing with them as just numbers. So I'm going to take care of it down here, though. We have 3 to the third power, right? So I'm rewriting. So let's see what we have. We have 27 to the fifth power, right? I'm going to put parentheses there to make this a little bit easier to see. I'm going to rewrite the 27 as 3 to the third power, but that still has to get raised to the fifth power. And because, again, I have one base with two exponents, I will multiply those exponents together. And so I'm going to get u to the fifth power, v to the fifth power, over 3 to the 15th power, because I'm going to multiply those exponents together. And I believe that would be an acceptable way to leave the answer. It meets all the criteria. One of each variable, no negative exponents, and we simplified the number. All right. So I think this would be a good opportunity for you to try one of these problems. So this problem is pretty similar to the one we just did. So why don't you pause the video, give this problem a try on your own paper, then resume the video to see how you did. All right, so the first thing you should have done with this problem is simplify it like we did the last example. Now this time the numbers don't reduce, which maybe is kind of a nice thing. It's one less step we have to worry about. But the variables will. So let's go ahead, and they don't reduce, but we can simplify the variables, right? So let's go ahead and deal with x, right? We'll do the same thing we did last time. So the 5 will stay on top. The x, the base, will not change. We'll take the top power, which is negative 1, minus the bottom power, which is negative 2. And then we'll do the same thing for the y variable. The base stays the same. Take the top power. I guess I should have maybe mentioned this before I asked you to pause the video. If there is no exponent indicated, I think you guys probably know that, but it's an invisible 1. And so we'll take the top power, which is 1, minus the bottom power, which is 6. And that will still all be over 7 because the 7's not getting canceled out, so we'll still have a denominator in this case. Right? So we'll simplify, and then we'll bring that power of negative 5 back into the picture. And so this will become a plus here, negative 1 plus 2, which will make that a 1. So we get 5x to the first power, y to the negative fifth power, the whole thing over 7. So now I'm going to bring this back into the picture here. We want to raise this whole thing to the negative fifth power, so don't forget about that. So this time we'll distribute it. I guess this is a little bit different than the last example we did because we have a fraction still. But you apply this power to the top and bottom of the fraction. And you just distribute it to everything in the numerator and everything in the denominator. Right? Because it's all multiplication or division, we can just apply it to everything. So let's continue up here. We'll have 5 to the negative fifth power. We'll have x to the first power raised to the negative fifth power. We'll have y to the negative fifth power raised to the negative fifth power over 7 raised to the negative fifth power. We will simplify, so we will get 5 to the negative fifth power. Let's wait to do that. We'll have x to the negative fifth power because, again, what we're doing here is we are multiplying. One base with two exponents, we multiply those exponents together. Same thing here, we're going to multiply, and sorry, that didn't come out right. And we will get y to the 25th power. It'll be positive 25. Negative 5 times negative 5 makes that positive 25. Over 7 to the negative fifth power. Now to end this problem, we don't want to have any negative exponents, so everything with a negative exponent gets flipped over. So this will get flipped down to the denominator, this gets flipped down to the denominator, this will get flipped up to the numerator to make it a positive exponent. The only thing that's going to stay put is the y variable because it already has a positive exponent. We don't want to change that. So on top we're going to end up with 7, and it'll become a positive 5 for the exponent. And the y to the 25th power, which we left there. On the bottom we will get the 5, which will now be to the positive fifth power, and the x, which will be to the positive fifth power. And this meets all the criteria, right? We have one of each variable, no negative exponents, and we simplified the numbers to the best of our ability, and we don't want to multiply these numbers out because we'll just get these really big numbers. All right, so that ends the topic of exponents and dealing with expressions like we were just dealing with. There's one little side topic that's included in this section that we want to talk about real quick. And if you're in my class, there will be at least one example of this on the test. So you want to make sure you're ready for this. And it is scientific notation. So I'm sorry, it's a little bit out of the way there. Let me see. It just gets cut off just slightly at the bottom of the screen, so I apologize for that. But what you see there, I think you can kind of make out what it is. I don't know, maybe not. I'll write it for you when we get to it, when I read it. So scientific notation provides a method for writing very large or very small numbers, especially ones that have lots of zeros, in an efficient and easy to read format. So that format is this: d times 10 to the power of n. That's the way we set up our numbers in scientific notation. D is going to be a decimal number, so that's why I chose the letter D for decimal. It's a decimal number that has to be between 1 and 10. It can be 1, but cannot be 10. So has to be between 1 and 10. Typically it will be between 1 and 10. But if you have to choose between the number 1 and the number 10, you want to write it as a 1 instead of a 10. All right? And the way I like to do scientific notation is a little bit different than you might have learned it in class before from a different teacher. The way I like to deal with it is this way. If n is a positive number, then that means this should be a big number. So if n is positive, then your scientific notation number should turn into a large number. And if n is negative, that's what I have written here. If n is less than 0, that means negative, then that means you should be getting a small number. And if it's a small number, n should be written with a negative. Right? So keep that in mind as we do these next couple of examples. Positive exponent, big number. Big number means you should have a positive exponent for 10. And the same thing with the other one. Negative exponent is a small number. And a small number should give you a negative exponent when you're writing it in scientific notation. All right. I like that better than move the decimal to the left or move it to the right, because it's the opposite direction depending on which way you're going. So this is the same direction regardless. It's not maybe the same direction, but you can read this the same way regardless of which direction you're going in. All right. So let's take a look at an example. I'll show you what I'm talking about. So convert this number to scientific notation. We have 16 billion, right? That's what this is. It's in billions. So to write this in scientific notation, what we want to do is take the decimal, which is currently invisible, but located at the end of the number, and we want to move that decimal place until we get a number between 1 and 10. All right, that's getting this part right here. I want to get a number between 1 and 10. So I'm going to move it to the left. If I move it to the right, it's making it even bigger. I want to move it to the left to make this number smaller until it's between 1 and 10. So count how many times you have to move it. 1, 2, 3, 4, 5, 6, 7, 8, 9. I can't stop here because if I stop here and I put the decimal here, that gives me the number 16, which is not between 1 and 10. So we got to go one more time and put the decimal here so that we get a number between 1 and 10. So that's why we have that requirement, because that way everybody has to stop at the same point. If we didn't have that requirement that it had to be between 1 and 10, people could write these numbers in all sorts of different ways. So we're going to stop here, and that gives me the number 1.6. Right. Then this part's always the same for every scientific notation number, times 10 to the power of, and the power you want to raise the 10 to is however many times you move the decimal place. So we moved it 10 times. Right? It was 9 times up to here, and then this was the 10th time right here. So the exponent here will be a 10. And then the last thing you have to decide is, should that be a positive 10 or a negative 10? And here's where my rule comes into play. If this is a big number, the exponent should be positive. If this is a small number, the exponent should be negative. So this is a big number, which means we will have a positive exponent. And so I'm just going to leave it as a positive 10, and that will be the number in scientific notation. Let's try to do the same thing with this example here. Start from the decimal, which is located right here. We want to move the decimal so we get a number between 1 and 10. So I'm going to move it to the right. 1, 2, 3, 4, 5, 6, 7, 8. If I stop here, that's not good enough because I'll get 0.98, which is not between 1 and 10. So we have to go one more time, put the decimal right there. So we get 9.8. The times 10 part stays the same. The exponent here will be the number of times you move the decimal place. So it was 1, 2, 3, 4, 5, 6, 7, 8, 9 times. So I'll put a 9 there. And then the last thing I have to decide is, should that be a positive 9 or a negative 9? Well, this is a small number. Small numbers should have negative exponents. So I'm going to make that a negative 9. Right. And that way you don't have to remember, is it to the left or is it to the right? It's just small number, negative exponent. Big number, positive exponent. All right, let's apply the same idea to this direction. So here we're being given the numbers in scientific notation, and we want to convert them back to standard form, to decimal notation. So we're going to start with 3.94. I will move the decimal place 8 times because the exponent is 8, so we're going to move the decimal 8 times. But you have to decide which direction to move it. Do you move it 8 times to the left, or do you move it 8 times to the right? And so here's where that same rule comes into play. This is a positive exponent, which means I should be getting a big number here. Right? Big number, positive exponent, big number. If I move this decimal to the left, I will be making the number smaller. I will get a small number. I want to get a big number here because the exponent's positive, so I have to move the decimal to the right to do that. So 8 times, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to put the decimal place there. And any empty spaces that you have, you fill in with zeros. So I'm going to have a 0 here, 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 and here. All right, so that's going to be my answer. It's going to be 394 with 6 zeros. 1, 2, 3, 4, 5, 6. And that's the answer you want to type into Math Excel. It's really tempting here for me to use commas to make it easier for you to read, but I'm not going to do that because I don't think Math Excel wants you to use commas. Just type the number in without commas. I think that's the way you're supposed to do it. I could be wrong. Maybe they don't care about commas, but I'm going to leave it like that. Just make sure you count the number of zeros you're supposed to have when you're typing it in to make sure you have the right number. Okay, let's do the same thing with this problem, and then we will be done. I think this is the last page. So we have 9.88. The exponent is 9, so I need to move this decimal place 9 times. I have to decide, do I move it 9 to the left or do I move it 9 to the right? Here's how I make that decision. This is a negative exponent, which means over here I should be getting a small number. If I move it to the right, I'm going to make this a big number. To make it a small number, I need to move the decimal to the left. So I'll move it to the left 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, I got kind of sloppy there. And then I'll fill in the empty spaces with zeros. So I have a 0 here, 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 and here. And so that'll be 8 zeros that we have all together. So I'm going to rewrite the number to make it easier to see. It's decimal, and then 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8, and then we'll have 988 at the end. All right, so that would be this number in standard form. All right, so that concludes section R.7 on exponents.